Hi, this is Miss Ertl again, and I'm going to talk to you about what we call ideal mechanical advantage. For each of the machines that we are going to be using for simple machines, there's something called ideal mechanical advantage. It's called ideal because it ignores friction. Now, one of the statements on your note chart says that IMA, ideal mechanical advantage, is always greater than AMA, actual, because of friction. Because some of your pulling, some of your effort goes into overcoming friction, and so it'll always be less than we expect. Some machines, it's a bigger difference, like with inclined planes or ramps, there's a lot more friction because there's the dragging. With pulleys, gears, not as much, but still, if you were to compare what we expect it to be to what it actually is, the expected one, IMA, is always going to be larger. So we're going to look first at pulleys here today. And today, I think I already said it, we're going to do pulleys and gears. Pulleys, a pulley, you've probably seen it before. It's simply a wheel or a few wheels that have a string wrapped around them that then work together to pull something up or pull something down or move it side to side. Because it is a wheel, there is very little friction because rolling friction is very low. You can arrange them in different amounts. You could use a single pulley, you can use two pulleys, you can use a number of pulleys as shown in the examples here, A, B, and C, that there are lots of different pulley arrangements that you can use when you have pulleys. The IMA, the ideal mechanical advantage of a pulley, is considered to be the number of rope strands that are pulling up on the resistance or on the load. So if you look here at, for example, A, and if I can see that this is pulling up and this is pulling up. So this one would have a mechanical advantage of 2. This piece that is pulling down, and I'm going to use a different color for this so you can see it a little bit better, does not count. Because you're pulling down on it, it does not count towards the mechanical advantage. The one right underneath it would also is showing you, again, just showing you how that works with the mechanical advantage of 2. B, right here, would be also mechanical advantage of 3. This is 2. And C would have a mechanical advantage of 4. And so it would only take, as it shows in C, what that means is that if the weight that you're trying to lift is 20 newtons, it would only take you 5 newtons of effort because it is making you 4 times stronger. So if we go down to the examples, I have 2 different examples of pulleys. And again, this is ideal mechanical advantage. I guess I lost my eye on these. Is always the number of rope strands pulling up. So on the first example, this rope does not count. The first rope does not count. That pulls down. But I can see that 1, 2, 3 of them count. So this would have an IMA of 3. In this example, this one does count because it is pulling up. So that would be 1, 2, 3, 4, 5. So this one would have an IMA of 5. And so pulleys, you know how Ms. Ertl is always about showing your work. There's not a whole lot of work to show with this other than if you wanted to do the diagramming like I just did, that would count, but it's not required. Oops, sorry about that right there. So if I go down to gears, gears are ones where you have wheels working together, but they have teeth, and those teeth grip together. They can transmit motion from one spot to another. They can increase your force. They can decrease your force, depending on which one is considered the input and which one is the output. Now, in the example here in the corner, the output is the smaller one, but that's not always true. Sometimes the output is the bigger one. And so you just have to watch how they are labeled so that you know which one is which. Gears can also make things go faster or slower, because if you look at this diagram, the larger one on top would be moving a lot slower than the one on the bottom because of the difference in circumference. And so they can also change how fast something rotates. If you think about the gears on your bicycle, if you've ever ridden a bike and you've changed gears, how sometimes you have to pedal slower and sometimes you have to pedal faster, that is because sometimes it's on a bigger gear and sometimes it's on a smaller gear. The ideal mechanical advantage of a gear is the number of teeth on the output divided by the number of teeth on the input. What's a teeth? It's these little notchy things. So these little notches, every single one of those is considered a tooth. And so for this one, you're going to be doing some counting, so be careful, but you're just going to be counting teeth and dividing. So I have two examples here. And again, it is out over in. So if I have n out over n in, if this one is the output, I always mark the one that I'm counting from. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have an output of 12. And I don't have to label it because it's teeth. If you wanted to put 12 teeth, you could. Over input, and I'm just going to get rid of those so I can count easier for you. The input gear on the bottom is 1, 2, 3, 4, 5, 6, 7. So my mechanical advantage here would be 12 divided by 7. And that would give you 1.7 or 1.71, depending on how many decimals you wanted to do. And remember, mechanical advantage has no label. And so this one has no label. So this one would make my force 1.7 times larger. Okay. On the other side, n out over n in. The output is the smaller one. 1, 2, 3, 4, 5, 6. 6 over input. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which is going to give you a mechanical advantage of 0.5. So this one will make my force smaller. And you might think, well, why would you want to make your force smaller? The thing with machines is that you're not getting something for nothing. And if you remember back to the Eureka videos, they talk to you about that if it's increasing your force, so making it easier for you to apply the force, then you're going to have to apply that force over a longer distance. And so the one that makes my force smaller actually saves on the distance. So if it decreases your force, it also then decreases the distance that you have to apply that force. And now sometimes you want that and sometimes you don't, but that would be what's happening when you have this mechanical advantage of less than 1. And that's it for gears and pulleys.